Somebody has called me. Somebody spoke from my and announced that she was sick. So maybe it's today, but it's on
All right. Good morning. So welcome to day number 4 of our second workshop of this logic and algorithms program. And before we begin today, I would like to kind of remind you of why we're here. So, this workshop is on logic and algorithms and fine-grained complexity and query evaluation. And there's obviously a lot in common. And the general picture is something like this. So we have data stored in a database, like a graph. We have queries that are issued into the database, and we would like to answer the query as quickly as possible. The question of how is typically answered with some kind of fine-grained complexity analysis. So that's why there's the fine-grained complexity part of the workshop. The language that is used to express the query is typically logic. So that's the logic part of the workshop, right? And then sometimes the answer to a query is actually not what we want. Sometimes we do some computation on top of this answer of this query. And that was, Q2. And in day 1, we talked about non-recursive queries. So mostly like triangles or something. And then on top of that, we would like to enumerate every tuple in the answer one by one with constant delay enumeration. In day 2, there was the relational programming paradigm, when we do some kind of query on top of the output of the of the query, and that could be like training a machine learning model and so on. Day 3 was about how best to answer this query with distributive computation. That was yesterday. And today we are moving on a little bit to recursive queries. So this is a second, class of queries we have not looked into. And then tomorrow, I guess that'll be day 5. We'll think about, there'll be a presentation on how do you do this when there's an update to the database. We're not going to recompute the whole thing, how best to compute the answer if you knew the answer to the previous version of the database. Okay. So that's kind of, just want to sync up so that we don't get lost in the technical presentations. So without further ado, I will start today with Remy Wang, who is now an assistant professor at UCLA, and he is on one of our fellows. I will give the mic to Remy.
Okay, checking this. Can people hear me? Okay, thank you. And let me find the marker. And is it okay if I erase the part? Yeah. Okay, so my talk has 2 parts, and then the plan is that for the first part, I'll talk about actually still in the non-recursive case, right? Before we recurse, we have to think about a base case. So still in the non-recursive case, but in general, how do we make any program run fast? So talking about the idea of program optimization as such. And then to understand the big picture, so the goal of program optimization is that you give me an input program. So here is your slow program in some programming language. Just think of any arbitrary, Turing complete language or Turing not complete language, for example, C++, right? And now let's think of this entire whiteboard. So this piece of whiteboard as a space of all programs you can write in this language. And some of these are slow. So this is the one that you gave me. So this is probably not the optimal program. So our goal is to find from this space a faster program. That has the property that it's the same, it behaves the same as your slow program. So what that means is that for all inputs, we're going to produce the same output as your original program, right? So that's really the miles high level of program optimization. So this is challenging, just like in any combinatorial search. So we have a huge search space. So this search space contains the program we have as input, the program we want, and it also has other programs, like some programs that are slower. And then it also has program that run faster, but it's actually wrong, right? So we have wrong programs. So the challenge is really to kind of explore this huge search space in order to find a program that's both correct and fast. So our approach, this is work done with my collaborator Max in the audience here, is that we explore only part of the search space. So in particular, we only explore the programs that are correct. So we only explore the search space that covers all of the equivalent space of the program. So this will be a subspace of the entire search space. Right. And then basically, we traverse this space by rewriting the program to each other. So if we think of maybe the talk by Mahmoud a few days ago, so we saw that we have these algebraic expressions, these sum product expressions, and then by doing some algebraic rewriting, so maybe pushing the summation inside of multiplication and addings, so we can make the program faster just by doing these rewritings. So the idea is the same here. So we start with the input program, and then in general, we will apply these rewritings to get to the faster one. And then, so the first challenge here is that we want to somehow represent this search space efficiently, right? So in general, this search space, this space of equivalent programs, it can be infinite. There can be infinite many programs that are equivalent to the input. So we want to represent as much as this space as possible. So the idea is that, yes.
Just a quick question. I was just thinking, because you talked about wrong programs, is there any reason to look at them other than for approximation? Like if you think of approximation as the wrong answer?
Yeah, so there is another approach of kind of going at this program optimization problem, is that naively we think about enumerating all of the programs that run faster than this one until we find the correct one, right? So that's kind of an orthogonal search space. And then here we only explore the equivalent ones and to find a faster one.
That other one would be even harder, right? Because you would have to decide if they're equivalent, which is...
That's right, yeah. Yeah, it's not possible in general, but in some cases we can do that. Yeah. Yeah, so that part in programming languages, there's been a pretty popular approach called program synthesis, and that's basically what they do. So they try out different programs until they find the correct one. It sounds crazy, but it kind of works. Yeah. Okay. Yeah, so back to the problem of representing this search space. And by the way, ask as many questions as possible. I want to make this interactive, and I'll also ask you questions. So the approach we take is that we represent the search space with a tree automaton. So I finally say tree automaton. And then, so Marcelo, yes?
Before you run the search, how do you know that the search time is less than the time it takes to just run this local?
That's Good point. So sometimes we don't care. So sometimes we know that we'll run this program again and again and again. So it's better to spend more time optimizing it. Sometimes we do have a budget of how long we want to explore faster programs before we realize, oh, we're spending more time than actually running it. Yeah, so for the moment, let's just assume that the compile time doesn't matter. So we can spend as much time as we want in compilation and optimization. Yeah. Okay, so tree automata. So Marcello told us a little bit really quickly about tree automata when he talked about the sampling. And then here, let's do a slower introduction. Right. So tree automata, they are a generalization of the finite state string automata. And then it's actually pretty similar. So before talking about automata, let's talk about trees. So the trees we care about here are basically directed with directed edges and then labeled nodes. So only the nodes are labeled, and then the edges are not labeled. And then for each label, we also have a fixed arity. So in other words, we can think of these trees as kind of terms in a given grammar. So here's one example. We just have the multiplication, and then one child is constant A, one child is constant B. Right, so here, all of the inputs, we think of them, you can think of them as constants or variables. So these are zero arity function symbols. There's a zero arity function symbol. And here's a binary function, right? So whenever we see multiply, we must also see two children. So that's the kind of trees we're dealing with. Okay, so what's a tree automaton? So tree automaton basically defines a set of trees. So accepts a set of trees, just like a string automaton accepts a set of strings. And then, so it also consists of states. So we have a set of states. And then we also have a set of transitions. So I think usually they're written delta. So within the set of states, we can distinguish a few states, usually just one. So let's just assume we have one single accepting state or final state. So S A accepting state. And then the one difference between tree automaton and string automata is that we don't have a start state. So instead, we're going to have a transition function that transitions from nothing, right? So we kind of, without the input, we transition from a state. So yeah, and then for other transition functions, each transition function can transition from multiple states to a new state. So in general, every transition takes a tuple of states, S1, S2, all the way to Sk. And then we see a function symbol, some F, and then transition to another one single target state like this. Okay. And just to make this concrete, what the semantics of this is. So let's look at a few examples, right? So if I tell you this, we have a transition function that transitions from nothing to the accepting state upon seeing the function symbol A. So if we just say that this is the tree automaton we're dealing with, so can someone tell me what trees does this accept?
Just a single node labeled A.
Yeah, it just A, right? So similarly, if we have just a transition from B, well, from nothing via B to S of B. So this automaton over here with just this one single transition, it will accept the tree that's literally just this little constant b over here. So now a question to you is that what more do we need for this automaton to accept exactly this tree here? I need to add one more transition over here for it to happen. Can you guess?
Matrix.
Yeah, so it's going to be a transition that it's going to be a hyper edge because it's a transition from two states simultaneously. So we need to be in both SA and SB. And then we transition through, this is multiply, right, to the access of x. Right. So here, in general, we can see that we can turn any tree into an automaton that accepts exactly that tree pretty easily. So we just turn every single leaf node into a transition from empty through that node into some state. And then at every edge, we simply add a transition. So at every internal node, we add a transition that goes from the other nodes as states into that node. Yeah.
Clarification. Is there an accepting state on the board right now? If not, is capital A a bug?
Yeah, that's right. So so this should be little a. And then, so if we want to accept this tree, then the accepting state needs to be this guy over here. Yeah. Any more questions or?
The same question, but also, do you have like epsilon transitions where, let's say, if you need multiple accepting states, you just do a trick where you put them all into one?
Yeah, we can have them for this talk. It doesn't matter, so we can ignore those. Yeah. Okay, so right now our automaton is not very interesting, so it only accepts one single tree. So let's make it a little more interesting, right? So I'm gonna make it into a larger tree first. So let's say we have this tree, right? So we have A times B and divided by B. Right. And then so here, the first interesting thing we can do is that now we can have a little bit of sharing your automaton. So in order to accept this tree, we don't have to make another state for B, right? So we can reuse this state. And then what we do is that now, after we transition to the state for X, state for multiply, and then the state for B, we can add another transition into this division node. So let me touch this.
Excuse me, Remy.
Yes.
Do you consider the tree as ordered?
Yes.
Is it then okay to reuse SB?
I guess what do you mean by ordered?
Okay. Like left to right, does it matter?
Yeah, it does matter. So yeah, so A times B is not or this divided by B is not the same as B divided by that. Yeah, so reusing is also okay. So here. Okay, so after this, remember we want to optimize programs, right? So here we still have one single tree, so it's not very interesting. So to make it more interesting, we're going to start adding more programs into this automaton to represent a larger space. So one basic rule we can say that is that so if we have if we know B is equal to 2, so let me just change B into 2 all over the place for confusion.
One more.
Thank you. So if we know b is equal to 2, then a times 2 can be rewritten into a left shift by 1, right? So we have another node over here, which is s of I don't know, left shift, and then we have another one that accepts the number 1, and then we can go to here. And then to represent that these two are equivalent, so we can just merge these two states, where as I think Alden suggested before, we added a epsilon transition in between those states. So here I'm just gonna merge the two states. Right. So at this point, one important thing to notice is that now our states are representing equivalence classes of expressions. So here we basically say that this state will accept two different trees. So one is a times 2, and the other one is a left shift at 1. So they are both accepted by the states because they are equivalent to each other. So that's the key thing here. And then if we do go one more step, so we know that if something times another thing and then we divide it by the same thing, then we, assuming division by 0 doesn't exist, then we can merge this state with A itself as well, right? So let's make it a little complicated. So over here, we also have this one pointing here. Yeah, so now we have a rather complicated automaton. And then the cool thing to notice that now we are representing actually an infinite number of programs within this automaton, right? Because we can start from here, and then we can multiply by 2, divided by 2, and we go back here, and then we multiply by 2 and divide by 2 many, many times, right? Yeah. So here the accepting states, it used to be the state I just deleted over here, and because I merged it with the A state, so now the accepting state is over here. Yeah. Yeah, so that's really a small picture of how we do program optimization using this tree automaton idea. So the process is really simple. It just exactly like how you plant trees. So we first seed with a one single tree, right? So we insert this one single tree into the automaton to get an automaton that accepts exactly that tree. So that's step 1. And then step 2 is that we're going to grow this tree into a forest, metaphorically, by applying rewrite rules onto the automaton, so that it represents more and more programs in it. So after a while, after we apply this, maybe the automaton will stop changing. So that means we reach a so-called saturation. Or maybe we decide that, oh, this is good enough, so we have explored as many terms as we want, and then we run out of time, run out of space. So after a while, we decide to stop. And then at the end of this process, we basically have an automaton that represents a huge space of program, like we have here. So maybe it's not all of the programs equivalent to the input, but we're covering a pretty good space. Yeah.
Just about the intuition of the state is that basically each state is a unique arithmetic expression that's not equivalent to any other. So all the equivalent arithmetic expressions are in the same state.
Yes. Yes. Yeah. So all of the equivalent sub-expressions are accepted by the same state. So far, we're gonna break that in a bit. But for the final state, important point is that this final state only accepts all other programs that are equivalent to the original program.
So if there was another way to compute A, like in a more complicated way, that would map to that same SA state.
That's right. That's right. Yeah, as we see here, right? So A times 2 divided by 2 is the same state as just returning A as this. Okay. So this part is the problem of representing the space, but we're still not done yet, right? So it's cool that we can represent space, but we still need to get out this faster program that that we know is equivalent to the input. So that's basically the second part of this technique. So this kind of technique, the keyword to search for is equality saturation. So yeah, and then so after this talk, I'll also send a list of references of papers people can look into.
So is there a possibility of combinatorial explosion? Is that true?
That's right. Yeah. So as we do this, so although the automaton really compactly represents many programs, we still have a chance of exploding the automaton as we apply. So the key thing to remember is that every state represents one equivalence class, but if we just have exponential number of equivalent classes, then that will get us in trouble. So one example is that if we have a long chain of multiplies, and then multiply is commutative and associative, and if we just apply associativity and commutativity kind of blindly, we're going to end up representing the exponential number of permutations of this chain multiplication. Yeah, so even though we have compression, it's not kind of magic bullet. So that's one of the problems we're trying to solve, which is what happens when we do explode, and then I will talk a little bit about that at the end of this part.
But that could only happen if you have a loop, right? Like the recursive call or something.
Not quite. So even if we just have a long chain of like A times B times C times D times C, so if we have if we multiply like 10 numbers together, then there are like 2 to the 10, at least 2 to the 10 number of ways to multiply. Right? So if we represent all of them, then we're gonna have exponentially many classes. Yeah, so as an exercise, let's try to do that in the afternoon. So let's explode the board in the afternoon. Okay, so the second part is extraction, and let me figure out how to operate this. So just to make the intuition simpler, we can think about a different problem. So the problem we're dealing with here is that we have this automaton representing a different number of trees, and then we want to find maybe the shortest tree, the smallest tree in some sense, or the tree with the best cost in some sense. So maybe it's easier in the string case. So let's just work with maybe a string automaton, and then our goal is to find the shortest string accepted by the automaton. So let me just give you a random find state automata. So we have a start date over here. And then let's make it a little more interesting. Yeah, so here's a string automaton, and then it accepts a bunch of strings. So we have AD, a number of and the number is followed by D, and then B, C, I guess here's F, D, and so on and so forth, right? Yes.
So do we always want the shortest tree? The operators don't matter?
Yeah, so we can assign costs to the tree. Yeah, so similar here, let's say that A has cost 1 and B has cost 2, C has cost 3, etc., right? And then if we want to find the cheapest string, which is the string where the letters add up to the lowest cost, can someone guess what's the algorithm we can use to get that? Shortest path. Yeah. So really, if we find a path with the smallest weight, when we treat this as a graph from the accepting state to the final state, then that string basically has the length of that path. And then, in other words, if we want to find the cheapest string from this automaton, we can use something like Dijkstra's algorithm to get m log n speed for extraction.
That's making a linearity assumption that I don't think would hold in a lot of cases, though, right?
For programs in general, right?
The cost formulae of these expressions work.
Yes. Yes. So that's true, right? So here we have a constant cost per operator, right? So that's indeed a simplification. Yeah. So let's look at a general case. So first of all, strings are basically just unary functions, and if we look at general programs, we have functions with different arrays, and then things get a little interesting, right? So let's go back. Yeah, that's a little messy. So let me make a new automaton over here. So let's see. Yeah, I'm gonna go bottom up because it's a little more intuitive. So say we have A. And I'll leave out the symbols because they're not very important. And then the key is that we want to find some kind of sharing. Right? So, it's going to be a branch. So now we have a tree automaton, and then the intuition is kind of the same, right? So if we want to find, so actually this is still not very interesting because we don't have sharing yet. So let me point this to here. Yeah, so we have a tree automaton that accepts basically two different trees. So we have a choice between going here and going here in the automaton. And then if we want to find the cheapest tree, we basically want to find the cheapest hyperpath from the final accessing state to a bunch of leaf nodes, right? So for this case, if we treat the cost as the total cost as a tree, so if we have some more sharing, let's see. So if we have this one over here, a little bit more sharing. So if we take a left path and then we double count the cost of each occurrence of A and each occurrence of B, there is actually a M log n algorithm to do this extraction process to find a certain path. And then this is actually described by Donald Cruz in '73, I think. Yeah. So I'll send a link in the slides. And then this is basically what we implement, or what Max implement in our tool. So the idea is that we're going to assign initially infinite cost to every node, and then we'll try to find a lower and lower bound until it converges. Right. So this is Knut called it a generalization of Dijkstra algorithm. So the connection to the shortest path problem is very apparent. So that's an easy case. If we treat each duplicate node in the tree we extract as separate costs. Right. So a more interesting case is that sometimes we extract the final program as a DAG, which means that if we have sharing, if we reuse a node, then we're gonna only compute that node once. So we have a DAG of a tree as a compute graph. So in that case, we, I think, have preliminary proof that this extraction problem is actually now becomes NP hard, right? So it went from M log n into NP hard. So, yeah, so really the shortest path idea is that we start from the top node, accepting node, and then we're going to move to all children simultaneously. So from here, we go to here, and from here, we have to either move to these two children or to these two children. And then eventually, we need to sum up all the paths and then either repeat shared nodes or not repeat shared nodes to find the cost. So this should be 77. Okay, so it's NPR. So some earlier papers had the idea of maybe can we encode this as an interlinear program, right? So we have a few constraints. So one constraint is first we have to pick the final state. So the B is a Boolean variable assigned to every state and transition symbol. So we have to pick the final state. And then we have two more constraints. We have for all the function symbols F, transition F, we need to decide if we want to pick it or not. And then for each state S, we need to decide whether or not to pick it. So the F and S are defined as follows. So if we see a function symbol F, we say that if we pick the function symbol, then we have to pick all of its arguments. We have to pick all of its argument states. Right. And then, so if we pick a state, then we have to make a choice of which child of that state we want to also pick. And then under these constraints, we want to minimize the total cost assigned to the function symbols. Right. So here still we have this assumption of every function symbol has a constant cost. So to get over that, that's ongoing work. Right. So does this make sense to people? Okay, good. So that's wrong. Let's look at why that's wrong. Right. So if we look at where did our if we look at just this simple automaton, right? So we have position due to this, and then we have another one, and we have a loop over here. Right. And then finally we have accept. Right. So our constraint says that we have to pick the final state. So we pick this one, and then if we pick a state, we have to pick one of these children. So here we have one choice. So we're gonna pick this one. So if we pick a transition, we have to pick all of its children. So once again, we have one single choice. So we pick this one. And then now is where it gets interesting, right? So this state has two transitions that goes to it. So we can either pick the F or pick the B. So let's suppose we pick F, right? And then here, because we enter the loop, then we can kind of satisfy all our constraints without being grounded. And this is not a valid program because it doesn't really take any input, right? It just is F applied to itself and to nothing, right? So in fact, if we just encode this into ILP, we will get invalid programs. And it actually took us a while to find this bug, right? So the answer is actually in logic programming. So instead of integer linear program, we actually needed to encode this as an answer set program. So I think So this is really the example that taught me the difference between IOP and ASP. So
Remy,
yes.
can we fix the linear program by adding like a depth value that is associated with every?
Yeah. So that's one fix. But in practice, that kind of runs really slowly. So you can basically order the nodes in some way. Right?
Yeah, so that we always the depth of a new node is higher than the depth of its children, and that's how we can.
That's right. Yeah, so that's one. That's a correct fix, but it runs kind of slowly. Yeah. Yeah. So this is a very quick introduction to answer-set programming, and let me see. Oh, I'm already out of time. Is that right?
For the first part, yeah.
For the first part.
Take a little break.
Sure. Yeah, this is a good place to stop. And then yeah, let's come back to the ASP after the break.
So we have a 5-minute break. We have to do some